All right, so now I'm recording the workshop, and I just put a disclaimer. Those who don't want to re-record that can. Please can watch us later, but we're going to use this as an educational resource and hopefully post it on social media. So, with that, Oliver, take it away, and I'm looking forward to learning about text embeddings.
Cool. Thanks, Nick. Let me go ahead and share my screen for the presentation. I think I'll need permission to share a screen.
Oh, yeah, yeah, you got permission.
Cool. I'll try that again. Cool. All right, so you all should be able to see the first part of my slide. Is that showing up for everyone?
Yep.
Cool. All right. Yeah, so welcome everyone to my tutorial on representing text with word embeddings. The outline of today is going to be a quick presentation on what word embeddings are, why you might want to use them, and then a little bit on like how we can train them. And then I'll go through some live coding exercises on taking corpus from PubMed, training some word embeddings, and visualizing them as well. So that'll all be done in Python and Jupyter. You don't have to follow along if you don't want to. You can definitely just watch. And then I think there's also a GitHub that I'll put the notes and then all the code up on as well. So the goal for today is to understand why text representations are important and a few different ways that you can represent text. And finally, I'll go over some Python libraries to leverage text to be able to learn word embeddings. Let's fix something really quick. Cool. All right. So, I mean, your question is, why might we even want to represent text? Well, in quick summary, text encodes a lot of important information. We use it to store and pass around this information as well. It's a big part of how we communicate. You and I can read text, we can understand it, understand what this information is because we know what the symbols on the page mean. We can take into account information like context of where the words occur, who's speaking, as well as world knowledge. That's just like knowledge about the world around us and how that impacts how we interpret text. But there's a lot of text out there, and it would be hard to, for each and every one of us to quickly go over all the text when we're, say, looking for a specific scientific article. And that's why it might be useful to be able to do this in an automated fashion or trying to teach machines to read text like we do. And this is another field called natural language processing, which is a subfield of machine learning. And a great quote that just kind of encapsulates what natural language processing is natural language processing is a term that refers to the automatic computational processing of human language. This is from a textbook called Neural Network Methods in Natural Language Processing. If anyone here is interested in learning more about NLP or deep learning, this is a great book to start with. I think it's pretty accessible. So as mentioned, NLP is a subfield of machine learning, meaning that natural language processing develops a lot of theories and approaches to automatically compute and extract information from language using a lot of machine learning techniques. These are techniques that I think a lot of us may have come in contact with, like linear and logistic regression, or support vector machines, or decision trees. But we all do actually still interact with natural language processing even outside of our own work. So with a Google search, we see it in advertising, or autocomplete when you're texting on your phone or anything like that. So there are a lot of different use cases for NLP. You might want to use it for clustering so that you can find similar scientific papers if you're doing a literature review. You may want to identify whether or not a certain concept appears in a document. So if you're searching for concepts related to social determinants of health, NLP can help you do that quickly. You can also use NLP to generate new text given textual input or other kinds of data. You can go even more fine-grained and identify spans of text or segments of text that contain key pieces of information. You can identify relationships between words and words within a sentence. So maybe an adjective and what word this adjective is supposed to be related to. And there are many more other examples of what NLP can do. But in order to be able to leverage NLP to read over text and to extract information or do anything that you can see on this slide, we need ways to represent text in a machine readable format. So like mentioned, you and I can look at a screen and understand what the words are, but there needs to be a little bit of processing to take the information you see on a screen or a piece of paper and put that into a format that computers can read. So this comes in, to the question of how we can represent text. So when you're representing text, it's important to, you want to basically extract the important properties from a piece of text, and what you consider the important properties is really dependent on your use case. So the kind of information you might extract from a piece of text to represent it is going to be different for if you're doing a literature review versus if you're looking for certain medications in a clinical note. And so some considerations might be which words are present, where are these words located in the text, who is the speaker, a little piece of information like that. And so one of the main ways of representing text is something called a bag of words representation. So in a bag of words representation, you represent a piece of text as a list of indicators, where 1 represents if the word is present and 0 represents the word is not present. So for example, here we have the sentence, "It's a good day to be indigenous," and you would represent this using the table or list that you see, I think, on the right of your screen, where you see that the words indigenous, day, it, and be all have a 1 indicating that they're present, while the words old man coyote all have 0, so they're not present. An important thing to note here is that the order of the words in the list doesn't match the order of the words that you see in the sentence. So all we're doing is representing whether or not these words appear in the sentence, but not representing where they appear. And so you kind of lose a little bit of that information using this kind of representation. You can also represent words instead of using indicators, you might represent them as counts. So how often does a word appear? And related to bag of words, there's something called term frequency, inverse document frequency, which I won't go into, but it's a method that is similar to bag of words, but it addresses how seeing unimportant words too often can kind of throw off your textual representation. Let's see. So as mentioned, we lose a little bit of information with this representation. We don't know where these words are occurring specifically in the document. And I'll go over later when I talk about some drawbacks of bag of words representations, why we might not want to be able to represent that information. So a good way to think about this kind of representation for text is thinking about each word is represented by something called a one-hot embedding, or essentially a vector or a list where only 1 index in the list is 1. So as you can see here, we have essentially the same representation if we parse apart each word in that sentence. So the representation for the word indigenous has a 1 in the very first index and 0 everywhere else, while the representation for the word day has a 1 in the second index, but 0 everywhere else. And so what you do is you add those together in order to get the table that you saw here. Let's see. Yeah. And so there's definitely some drawbacks to doing this. As you'll notice, the vocabulary or the kinds of words we're dealing with here only include indigenous, day, it, old man coyote, and the word be. That means that there are some words that we're not going to be able to represent here, or we're choosing not to represent. And that also means that if we want to add in more words, then we have to increase the dimensionality or the number of elements in our lists. So that kind of brings us to the drawbacks of these words. So I'm actually going to talk about the second point here. They're a little bit out of order. So if you want to expand a vocabulary, if you want to add in more words, then we'd have to go in and add in an extra space at the bottom of this list for that word. And so that means that the larger our vocabulary gets, the larger our word representations get. And that can be an issue when you're computing or when you're trying to store this information, because you're storing a lot of information that you're not exactly using anymore. And as mentioned, we lose some information when we're talking about where these words occur in the sentence. So we could store the information, but then we'd need, in the list on the right side of the screen, we would need a new index for every word, for example, the word indigenous, for every word that's going to occur in a sentence. So instead of just having one index for the word indigenous, we might have 10, 20, 30, depending on how large your text is going to be. And again, you run the same issue of an explosion of dimensions, which can be hard for computation and storage. Finally, it's not exactly obvious how you'd measure similarity between these two vectors. So this one's kind of a difficult example, but let's say we had the words kitchen and sink. I think a lot of us can say, well, they are similar, they're not the same, but they're similar because sink is a component of a kitchen, and they're related in that way. But if we were representing kitchen and sink using ones and zeros, there would be no measure of similarity that could capture how similar they are. In fact, the word kitchen and sink would be just as similar as the word kitchen and bamboo using this kind of representation. So that means that a way we might want to represent word embeddings is something that, or represent words, is a way that they can capture our understanding of how similar they are. And this brings us to the idea of word embeddings. So word embeddings are known as dense representations of words that capture meaning. So dense representations means that instead of them being one hot or just ones and zeros, they're actually lists or vectors that are full of numbers and fractions. So, and you'll see that a little bit in the coding portion. And when we say they capture meaning, well, meaning is a loaded term. So what we mean by meaning here is by this quote by John Rupert IV, which is a very old linguist, but he says, "You shall know a word by the company it keeps." So when we say meaning, we mean that if two words appear in similar contexts, that is, if they have similar words surrounding them, then they should have similar meaning as well. And so that is the idea behind word embeddings. Now, word embeddings, like I said, are dense representations of vectors or lists. So that means that they can have they can be multidimensional. But an easy way to think of them is 2 dimensions. So here is a toy example of what 2D word embeddings might look like. So these are points in space, the X and Y coordinates. And we can see that, I don't know if you guys can see my mouse, but up here in the top, we see these yellow ones are things like refrigerator, oven, LG, GE, and microwave. So these are appliances and companies who make appliances. While over here, these light blue ones are like kitchen, vanity, sink, bathroom. And these are all related to each other. And they're kind of related to up here. That's why they're, or kind of related to these yellow word embeddings. That's why they're close in this 2D representation. And then they're far away from a word like sprinkler or something like that, which would make sense because you wouldn't often see the word vanity or sink occurring in a similar context as sprinkler. Let's see. Okay, so that kind of brings us to the question of, great, like we can represent words in this dense representation where they have meaning that kind of makes sense when we look at them. But how do we go about learning these kinds of representations? There are many different algorithms to do this, but the one that I'll be talking about today is something called Word2Vec. So Word2Vec is the name of the algorithm that allows us to go and learn word embeddings and kind of encode their meaning in these word embeddings as well. So it relies on the idea that we're going to use the context of a word to try and learn its embedding. And I won't go too deep into the math here, but I'll provide notes later that have more reading on this if you're interested. But the intuition is that we want to be able to use the word embedding representation to try and have some understanding of the words that appear around this word. And if we can do that, then we've essentially captured information about the context of this word. So there are 2 different ways of doing this. One's called continuous bag of words, or CBOW, and the other one's called skipgram. So CBOW uses the surrounding word representations to predict the word at the center, while skipgram uses the center word to predict the words around it. It's probably a little bit hard to like understand exactly what that means because this is just like words on the screen right now. But there's a couple examples of what this can look like. So the idea is that if we're doing something with CBOW, we want to be able to predict a single word given its context. And so that's when you use a sliding window. This is a sliding window size 3. And then it goes and finds, okay, well, the two contextual words are thou and shout. And then we want to be able to predict the word not from those two word representations. And what you do is you go ahead and you create a data set out of this to be able to learn, using machine learning, good representations. So you continue sliding this window across the text in order to create a data set. So yeah, so you would create this data set, and then using the algorithm of CBOW, go ahead and learn what these word representations are. Skipgram is similar, except skipgram is going to try and predict what are the surrounding words given a center word. So you can see here that the sliding window is a different size now. It's takes in 5 words, and it's trying to predict, or trying to take the word not, and then predict what are the words that appear on the left and the right of that word. Yeah, and so in doing this, we basically create a data set that can let us train a model to learn word representations or word embeddings that contain this kind of information in. So a couple of implementation details. The learning is done through, like I said, machine learning. It uses a small neural network that takes the word embeddings and tries to learn better representations in order to predict the surrounding words given a center word, or to predict the center word given the surrounding words, either skipgram or CBOW. And I won't go, we won't have to go into the details of like how that's done exactly, because the packages we're going to be using actually do that behind the scenes for us. Another important detail, well, not so important, I guess, but the interesting detail is that the way we start off doing this is by randomly initializing a bunch of word embeddings and then kind of shifting them around in space so that we can perform the task of CBOW or skipgram better. Cool. So that is the presentation part. If anyone has any questions on word representations, why we might use them, more examples of how we could use them, go ahead and let me know in the chat, or you can go ahead and speak up as well. In the meantime, I'm going to stop sharing and get the coding portion ready. So if anyone wants to bring up their Jupyter notebooks or go ahead and look at the GitHub, now would be a good time to do that.
Hi, this is Francisco. I emailed you about not being able to open it. I know you gave me some help. That was helpful, but I still wasn't able to figure it out.
Okay. Yeah, no worries. What was going on?
I think you're right. Basically that, I guess because you had it as a Linux file and then in Windows, I can't open it, the XML. And you had given a suggestion about changing the encoding, but I just don't know where to put that.
Okay.
Where, yeah.
Yeah. Can you put in the chat the snippet of text I sent you really quickly? Yeah. So I can put that in here too. And someone asked for the GitHub. Okay, cool. Jordan got it. And then when I share my screen, I can show everyone how that's done really quickly. Yeah, so sorry. I guess Jupyter Notebook might be kind of new to some people. It's kind of daunting, but it can be nice to use if it's if you're just learning Python. I'll show you how to do that. Let's see. Cool. So let me go ahead and share my screen. Desktop 2. Can everyone see the Jupyter Notebook that I have open?
Mm-hmm.
Yeah. Cool. Let me look up something real quick. TF8, read Python. Sorry, as soon as I brought up the screen share, I lost access to the chat, so I'm just looking up something really quickly. Okay, this will hopefully fix your problem. If it doesn't, let me know. Well, yeah, if it doesn't, we can speak offline about it. Okay, so everyone can see the notebook. Quick intro to how you use these notebooks. Oh yeah.
Sorry. Yeah. Hi, I'm Daniele. Just one thing about the notebook that I had to do on my computer is that on that line with open in the XML file. So the inner loop, the second loop, basically, I had to specify encoding CP1252, or else I would get an error that I couldn't encode one character.
Okay. That might be the problem that was being discussed, actually.
Yeah, I was trying to do encoding UTF-8, but I would get another type of error.
How did you type it? Was it CP?
CP 1252.
1252. Okay. Are you using Windows as well?
Yeah.
Cool. So this might be a problem that people who use Windows are encountering, just because I'm using Linux and there might be some encoding issues between going back and forth. So if anyone is using Windows, you might want to add this little section to your code. But without it, I think you should still be able to run everything, because...
I also added, after that encoding, errors equals replace. I don't know if that matters. It was just like what I found online that some guy did, and it worked. I don't know if that, the other thing about errors is necessary, but I added it.
You added, oh, you added like some kind of another argument here?
Yeah, I can share my screen if you want to, just to show.
I'm not sure if you'll have permission to, I can add it here though, so other people can see it. What would you add?
So errors equals between the, replace? Replace, yeah, like that.
Okay, cool. Yeah, so anyone using Windows might want to add these in. That being said, I don't think you'll have to, because a lot of the code that we need is already in the notebook itself. Yeah, sorry, you won't need this section to run anything, because the data that you need is provided in the GitHub. But these are good things to know. So the first thing we'll want to do is go ahead and run these imports. So then this will allow us to use the Word2Vec model that GenSim has, as well as some tokenizing and sentence splitting methods as well. And then we want to import NumPy, which will allow us to do some easy math. And then you can come down here, and then what we're going to do is we're going to read the information from, I'll show you guys really quick. We're going to read the information from data, which you should have a PubMed sample.txt. So we're going to read that into a list so that we can store the each abstract in the list. And the way we're going to do that is by initiating a list really quickly, abstract lists. And then we're going to go ahead and open the file. And that's located at data / PubMed sample.txt. We want to indicate that we're opening this file to read it. And then we're going to call it abstract file. And then we're going to iterate through this file using an iterator. So for line in abstract file. Then we're going to take abstract list. Also, if this is going too quickly for anyone, anything, just let me know. Abstract list, and then we're going to append the line. And then we're going to call strip on that line as well. So what strip does is it removes any leading or trailing white space, which is just not really necessary for what we're doing here. And then to make sure everything works out, I'm going to go ahead and print out the length of that. Out abstract list. And I guess it would probably be helpful for me to let everyone know how to run abstract, or these cells as well too. Let me just do this. So in order to run a cell, you want to click in it and then hit Shift Enter. And then if everything works, you should get this printout. Hopefully everything worked. And then just to do a quick sanity check, we can go ahead and print out the five first abstracts in there. So we get something about alpha bisolol. Wow, I should not have even read that because I have no idea how to read that. And then another abstract about assigning immunological properties. Yeah, so this looks good. All right. Is everyone okay on that part so far? Let me know, and then I don't have
just a
access
minute.
to the chat. Yeah.
I'm just still writing. Okay,
No worries.
I'm on the print line. Yeah.
Okay, cool. Yeah. Again, please let me know if I have to slow down or anything. Let's see. Yeah, and then also I can't quite see the chat when I'm sharing my screen, so if anyone just wants to let me know if there's any questions in there or anything. Okay. So the next step is that we have to process our data into sentences. So Word2Vec was originally designed to only work with sentences, because if you want to understand what a word means by its context, maybe you define context as only being the words that appear with this word in a sentence. That being said, you could define context as being in an abstract or an entire document or a paragraph. It depends on your use case. So just because it's useful, I think it's good to be able to chunk up our abstract into sentences using Jensen. So we're going to do that using this function called split sentences, and you can see the documentation here. I'll go ahead and type out what has to happen. So we're going to iterate through our list of abstracts. So for abstract in abstract list, we're going to instantiate a variable called sentences, and then we're going to set that equal to the function split sentences. That's going to take in a single abstract. So again, we're looking at a single abstract in our abstract list, throwing that into the split sentences function. And a cool thing you can do with Jupyter notebooks is if you have a function here, you click within the parentheses, hit Shift Tab, it'll give you a doc string on what that function does. So this will split a piece of text into a list of sentences, and then it tells you the parameters to put in. So all it takes is a input text. So then we're going to go ahead and capture that. So for sentence in sentences, the spelling here might get kind of weird. So you just gotta make sure that you don't do for sentences in sentence or anything like that. It'll just throw some weird errors. Then we're gonna take our list, sentence list, and then we're gonna append to it. This just tacks on at the very end, the sentence. And then for a quick sanity check, let's print out how many sentences we found. And then just a quick note, sentences extracted. Let's go ahead and run that. Cool, so we found a ton of sentences, which makes sense. There are more sentences in abstracts because each abstract has at least one sentence. Let's see how well this did. So we see that the first one it picks out is this sentence from our very first abstract, and then the second one is also from the first abstract. Let's do a quick sanity check and see how that looks. Yeah, that makes sense. It should be the end of a sentence, also the end of a sentence. Yeah, so whenever you're working with a sentence tokenizer, which is what split sentences is technically called, you're gonna wanna make sure that the sentences it extracts make sense. One caveat is that a lot of these sentence extractors were made to work on general text, so something like Wikipedia or a novel or something like that. So they may not work as well on biomedical text, so scientific text, and I can assure you that they work absolutely terribly on clinical text, which means you have to do a lot of legwork to get that stuff to work.
Hey,
okay.
Oliver.
Yeah.
So when you say it doesn't work well in different kinds of text, do you mean it will split sentences where they're not supposed to be split and things like this?
Yeah, yeah. Yes, that's a good question. So like it'll technically work, like it'll run, but you're right, it'll split sentences up early, or it'll like make very long sentences. And that's because the way these methods work is sometimes there are a bunch of rules, and they're like, well, if you see a period and then the next letter is capital, that means that you just encountered the end of a sentence.
Right.
But you also might see a lot of exceptions to that, especially if the text you're looking at doesn't follow great grammatical rules or great structure, especially in clinical text.
Right, right.
Yeah.
Cool, thanks.
Yeah, no problem. Okay. So the next thing is that we split up our abstract and sentences. And the next thing is that GenSim also requires that each piece of text that we're going to be working with is represented as a list of tokens. So what that means is that this string right here needs to be represented as a list of little strings. So this might be one string, this would be another string, A might be another string, and that would be a list of all those strings. So GenSim has another function called tokenize by word, which takes in a piece of text and then returns to you, similar to the previous function, it's going to return a list of strings, which is exactly what we need. So let's start off doing that with our abstract first. So we're going to iterate through the abstracts again for abstract and abstract list. Then we're going to take, we're going to create a variable called tokens. Right. This is also a little bit of a jargony thing that you'll see a lot in natural language processing. So a token is, it's easiest to think about a token as essentially a word, but tokens can also be subwords. So this would be a token, but then so would, if we split it up into out and then standing, each of those would be their own token as well. Token is just a chunk of, or a small chunk of text, essentially. So a phrase, a word, a subword, something like that. Yeah, so tokens is going to be equal to tokenize by word. Let's see, I'm going to spell that right. Tokenize by word. And then we're going to add in abstract as the first sentence. So, or as the first argument. Really quickly, let's go see what tokenize by word does. You can also click on this and it'll take you there, take you to the document string as well. Tokenize input text, transforms. So this one is important to note. It transforms it to lowercase. So you remove all the uppercase stuff, and it removes accentuation and things in its acronym set. So all it takes in is a piece of text, and it's going to return something called a generator. So anyone new to Python, a generator is something that you can iterate through in a for loop. I won't spend too much time on this because there are other things we need to get to, but you can turn a generator into a list, which is something that we want to be able to deal with by just saying, so this is going to return a generator, and then when it does, we're going to wrap that in another function called list. And what that's going to do is it's going to turn that into a list, which is something we can work with. I know that's probably a little bit hand wavy for people, but just because of the time, I won't go too in detail on that. But feel free to ask me later if you need more details on what's going on there. Yeah, so next, we're going to go ahead and take our abstract list tokenized, and then we're going to append our list of tokens that we just created. So let's go ahead and do that. So this can take a little while to run. The reason for this is that tokenizing is kind of an expensive step, and we have a lot of abstracts to tokenize. So let's go ahead and look at what we got really quickly. I'm going to skip over this cell for now. But so abstract list, the very first one is this. Let's see what we got. So I split this up into alpha. Visible has a primary. So we see that this is a list of these singular tokens. And it captured looks just about everything in that abstract. we can do the same thing for our sentences. And I'll just go through that really quickly. It's not too much work. It's going to be a lot of the same stuff we just did. So we're going to do for sentence in sentence list, tokens equals, we're going to use that list trick again because it returns a generator, tokenize by word, and then with this time we're going to throw in sentences or the sentence. And then we're going to append this return to the sentence list. Tokenized.append tokens. Go ahead and run that. One quick thing to note is that if anyone's used to like programming in maybe R or MATLAB or God forbid C, you don't have to instantiate a variable outside of the for loop. You can do that within the for loop and just refer to it. Python's pretty chill with that. Also, because this is in a for loop, this variable is getting overwritten like repeatedly every time the for loop is called. So that means like this is getting updated, and then we're appending an updated value to the abstract list. Just something quick to know. Okay, so now that we've got the pre-processing out of the way, we can actually get to training some word embeddings. How's everyone doing so far? Is everything okay with getting this list? Cool.
That looks good.
Cool, cool. All right. So we're going to use the word2vec function from GenSim. The documentation is here. This one's a little bit more complicated. It actually has a lot of different parameters that you have to use. But well, let's go ahead and take a look at the document stream. So this tells you a little bit on how to use it. You have to put in a sentence. You can also put in a corpus file. So what this means is you can provide a list of sentences where each sentence is a list of tokens. Kind of confusing, but that's how they work. That's how they take in things. You can also provide a corpus file, which we're not going to use, but I'm going to assume is a text file possibly. And then this size is how big do you want your word embedding to be? So how many dimensions? You can have 2, you can have 500, you can have 100. Alpha is something that's specific to the word2vec formulation. I won't go over that because we can go with the math. Window size is essentially when you're generating your data to learn the word embeddings, how much context do you want to take into account? So the larger this is, the more context you'll take into account. Minimum count, so how often should a word appear for you to generate a word embedding for it? So if a word appears only once, maybe we don't want to learn that word embedding because it might be difficult to learn that word embedding. It might be noisy just because there's not a lot of information. Max vocab size is just how many words do you want to learn, or how many word embeddings do you want to learn. Let's see. I think that's most everything we're going to be using. Yeah. Let's see what else. Yeah. I think SG, if you set that to 1 or 0, it dictates whether or not you're going to be using the CBOW algorithm or the skipgram algorithm. In practice, both algorithms are usually fine. You get pretty similar word embeddings using either one. And then a quick one, seed. I mentioned that we randomly initialize our word embeddings. This will dictate what the random initialization should look like so they can replicate studies. And then workers is just how many cores or how many CPUs you want to be using to do this. So go ahead and type this in. So the first argument is sentences. And then we're going to set that equal to, let's work with our abstract list for now. List tokenized. And the way you put in multiple arguments into a Python function is you just put a comma there, and then you can input more information. So the size of our word embeddings is going to be, let's say 100. Let's say the window size, let's just leave that equal to 5. The min count, let's use 1 because we can be greedy. And then the number of workers. So this is dependent on your computer. I think if you set to 4, most of you should be safe. If you set to too many cores, like it's fine. It won't blow up your computer or anything. It just won't use that many cores. Your computer might slow down a little bit, but you'll get it back eventually. And then iter. I didn't explain iter. So iter means, I think that is how many times should you iterate through the data? Yeah. So the way that a lot of neural network models work, which is what Word2Vec is it iterates through the data multiple times. And each time it iterates through the data, the hope is that it gets better at learning what it's supposed to do. So in this case, word embeddings. So we'll just go ahead and iterate through our data 5 times and then hit run. And then if you're getting nothing in the output and this turns into a star, that just means that Word2Vec is running in the background. And that's fine. This might take a while, so probably best to be patient with it.
Oliver, I have a question.
Yeah.
So one of the argument iter, it seems like it's also a special term in Python, right?
Yeah.
So I wonder how Word2Vec can disambiguate whether that's an argument or the actual special term.
Yeah. So Python has special terms like Nick mentioned. And one of these is called iter. Another one is called stir or list. And you'll see that when these, in some text editors like Jupyter Notebook, they'll have a green highlight like that. And that means that you've encountered a special word. Python is really loose with this. So you can overwrite these special words or these special terms and everything. And that can actually mess up a lot of stuff. But we're safe here because there's something called scope. And long story short, what that means is that Word2Vec is going to take in this special word called iter, and within that function, it's overriding what the special word means for Python. When you return from that function, that's no longer true. The special word is restored to like what it meant before, and we'll be okay. Best practice is not to do what Jensen did here and use iter like that. You actually would probably want to just use like iters or something just to be safe, because that can be like a really sneaky bug if you like change iter and then later on you're like trying to do something and you just see weird things happening. This can be the case sometimes. Just because we're running out of time, I'm going to skip over doing this for the sentence list that we have as well, but it would be the exact same formulation, except this would be a sentence list tokenized instead. So hopefully this stopped trending for everyone. And now we can go ahead and start looking at like what this actually is. So again, you can go to the documentation here and look at what was returned, but we can also just do something quick and dirty in Jupyter Notebook. And you type in the object model.abstract, and then you put a period. I think if you hit tab, yeah, you hit tab. Yeah, just tab. And this goes, so this list right here is actually a bunch of either functions or properties that this object has. So this can be like information you can access from it. So alpha was a setting that that was set in Word2Vec, and so you might want to view that later. Corpus count might have something to do with how many tokens, how many observations are in there, something like that. Just a little piece of information like that. Now this is a lot of information. Most of it we don't need. We just want to be able to go and extract the embeddings actually. So to do that, we're going to run model.abstract.wv.wordEmbeddings. Go ahead and run that. And then we can look at, so the word embeddings that returns are actually NumPy arrays. And then we can call normal NumPy functions on that. So we go ahead and run this. And this may not mean a whole lot. So let's go ahead and add a cell down below this and just run this again. So these are word embeddings. Also, again, kind of hard to understand what they are because like those are just numbers, but to a machine, this would be pretty useful. But what this means is that we have 49,000 words in a vocabulary, and we have 100, and then each of these words has a list or a vector of dimension 100 that represents it. And the reason we have so many is because of this argument right here. All we said was that a word has to appear at least one time, and we'll count it. We'll use it as a, we'll create a word embedding for it. If you raise this, then your word embeddings, the vocabulary will get smaller, which maybe you want, maybe you don't want. All depends on your use case. Okay, so.
Just one small observation. Everything was the same from until this point, but when I see the shape of the embedding vectors, I have slightly more words instead of like
more words.
Yeah, I have like 49,701, and also the embeddings look slightly different.
Yeah, so the embeddings, that's okay if they look slightly different. Because like I said, the word embeddings are randomly initialized, and so you're going to get a little noise in them. But the hope is that every time you do this, they should be more or less the same or like pretty similar.
I thought that because we set the seed, they should be this. Oh, we didn't set the seed, right?
Yeah, I don't know if it sets a seed for us or not. Well, okay, then, so then the whole seed issue is also depending on the operating system you're using. So if you're using Windows, Mac, Linux, even differences within those, the seed might also like be slightly different. But the hope is that more or less these word embeddings should be the same. As for having more vocabulary, I'm not entirely sure why that would happen. The tokenization might have been different, but it shouldn't change too much. Okay, so a really quick way that we can go and look at word embeddings and make sure they make sense is by looking at, given a word, what are the most similar words to this word? And the way we define similarity is by looking at the word embeddings and using something called a cosine metric. So the way we do this is we say embeddings dot most similar. This is a function provided by GenSim. And then maybe a word we want to look at is dosage. So what are the most similar words to dosage? You should hopefully get something similar to this. If not, let me know offline and we can work on debugging that. But quick sanity check, a lot of these look like they're either drugs, a variation of the word dosage, doses, dosages, daily and night also makes sense. So like, you know, talking about a dosage of a medication, take daily, take nightly, something like that. So this is a kind of a quick sanity check that kind of makes sense. But why don't we run a couple extra ones just to make sure. Does anyone have any suggestions for a word they want to look at?
Virus.
Let's look at virus. Virons, influenza, antigen. I don't know what HBsAg is, but hopefully one of the smart people out there knows. These seem good to me, I think, you know, quick sanity check. I did a couple of these. Are there any more that people want to run? I found one that I thought was kind of interesting. Mouse is kind of fun. Chick, embryo, spleen, hamster, embryonic. I'm gonna guess that these are normal things you would run tests on, maybe. An important thing to know is that this is very specific to PubMed. So if we were to train these word embeddings on Wikipedia, I'm gonna guess that mouse would actually appear closer to, not embryo probably, but like a lot of other words like rodent or like maybe squirrel or something like that. Or maybe it would be computer mouse. Okay, we don't have a whole lot of time left. So I'm just gonna explain what happens here. So I took a sentence out of one of the abstracts, and the way we might represent this if we were using one hot embeddings would just be a list of a vocabulary size would be 49,000. And we'd have like ones where we see the word the, antipeptic action, stuff like that. When you're using word embeddings, you would actually just go ahead and add up all the word embeddings for this word. Is it okay if I go like 5 or 10 minutes over? Is that...
Yeah, sure.
Okay.
Yeah.
Problem.
Yeah. I'll just go ahead and show everyone how this works then. So to represent this, we would just say, let's say tokenized text rep equals tokenized by word. So what we're doing here, so I guess I should explain what's going on here, is we're going to tokenize our sentence up here. So we're going to call tokenize by word. Oh, and this would have actually aired out because I misspelled it. Tokenize by word, text rep, text to rep. And then what we're going to do is we're going to instantiate a blank word vector. So token rep equals np.zeros. And what this does is it just goes ahead and says, hey, NumPy, create an array of zeros for me. And we'll make that the same dimension as our word embeddings. And then for token in tokenized text rep, we're going to iterate through each of those tokens. And we're going to use another gensim function. So we're going to store that in token rep equals token rep plus embeddings dot get vector. And what this does is it takes a string, looks up the embedding, and returns it. So a token. Let's see if that runs. That runs just fine. And then let's go ahead and look at what we get. Again, you know, this probably won't be super meaningful for everyone just because it's like a bunch of numbers. But all we did was we took every word in this sentence, turned it into a word embedding, added them together. We could also average them, which may be a better representation in case one word appears a whole lot and we don't actually want that word to hold a lot of importance. So that's a way of representing text. Again, like, I know that's probably like not super satisfactory because I'm like, look, we can represent text and that's just like a list of numbers. Just so you know, you might use this in a logistic regression if, say, we wanted to like use a logistic regression to classify whether or not this sentence talks about DNA. What you would do is you would pass this into a logistic regression, and then the regression would learn weights to apply to each of these different indices in this array. And then it would classify for you whether or not the concept of DNA appears. Yeah, so that's one way you would use it. Okay. I kind of added this in this morning because I realized I promised I would talk about visualizing word embeddings. So if no one has it, it's new on the GitHub. I apologize for that, but you should all be able to go and grab it now if you want to. But I can just show everyone how we do it. You'll need a package called sklearn, which should be fairly straightforward to, either it comes with Anaconda or you should be able to install it similarly to how you install gensim. Matplotlib comes with Jupyter and Anaconda. All this is saying right here is this is saying, hey, Jupyter Notebook, whenever I tell you to plot something, plot it in the notebook. Again, apologize if everyone can't run this because I forgot to add this in earlier. This is a function that I found online from this source. They talk about how to visualize word embeddings using tsne. So tsne is pretty cool, actually. So it's a dimension reduction technique that will take something like a word embedding that's like 100 dimensions long and it's like very hard to visualize and reduce it to maybe 2 or 3 dimensions, and it's much easier to visualize. It does this using machine learning. And what it tries to do, I think in general, is it tries to preserve the neighbors of different words. And that can be important if we want to like make sure that the neighbors of a given word make sense. By the way, this is all up on the GitHub if anyone wants to copy this into their notebook or anything. Okay, so the first thing I'm going to do is we have a huge number of word embeddings, and that can take a long time to work with. So I'm going to go ahead and copy this code up here that we use to train word embeddings, and I'm going to train a new one. And then I'm going to say that the min count has to be at least, let's say 600. Because I want to make sure, I want to have very few word embeddings so they're easier to visualize. So let's go ahead and do this, and then I'll print out our new embeddings. Embeddings equals model abstract.wv, and then let's print out the size. Embeddings.wv, oh, let's see, dot vectors, yeah. Sorry, I just realized I'm mumbling to myself and like you can't hear what I'm saying, which is probably not super useful. All right, let's go and try and run this. Hopefully it runs faster because we're being a little bit more stringent. Cool. So this one only has 483 words in our vocabulary. That's gonna be much easier to work with. So we're gonna use this function that I got from here to try and plot these word embeddings. So what it does is you just type tsne plot, and then you just throw in the word2vec model. And let's see what we get. We get an error because I didn't run this piece of code. Let's try that again. Oh no, nope, it's because I spelled it. No, did I spell it wrong? No, yeah, here we go. Okay, so this should run now. Let's see if it makes sense. Oh, the reason it's taking so long is because, like I said, tsne is a machine learning model and it can be difficult to learn it, or it can take some time to learn it. I don't know how incredibly useful this is for everyone to look at. Let's see if we can zoom in on anything. Yeah, okay. So we see a cluster here, appears, may, should, can, could. That kind of makes sense. That these are words that kind of attenuate maybe you're talking about a hypothesis or results. Flow, pressure, arterial blood. You're talking about, I guess, like your artery system. And that this cluster actually appears close to cardiac and heart, which is this is a good sign. We see things like this looks like time, and then you can kind of pick out hours. I think there's days in there. I'm not entirely sure. There's a lot of overlap here. Chromatography, electro. I'm going to let the smart people read that because I don't work with that stuff.
Electrophoresis.
Yeah, thank you. So yeah, this is like a way for us to sanity check. Do these words make sense? Had, showed, calcium, sodium, ion. This actually looks really good. This is probably one of the better word embeddings I've ever learned because things make sense. I'm glad it worked out for this presentation.
This is really cool.
Yeah, I think that should be it. Does anyone have any questions or anything?
So do the colors of the points here represent anything, or is it just each word gets its own color?
That's a good point. Let me see. I think they have colors in here. I don't know if they, let's see, scatter, annotate. Yeah, I mean, I'm gonna guess that the colors don't actually have a lot because this was just done kind of like without knowing what the words are.
Right.
So it's probably just more like to more easily see them and stuff.
Right.
But you could, like, you know, if you knew a group of words that should group together, you could go and like add color to those and make sure they appear together and stuff.
Gotcha.
Yeah.
Cool. That's great.
Yeah.
Anyone got any questions for Oliver? Anybody?
I have a question of like the like using this for like in practical purposes. So I imagine what it would do is, for example, if you want to do literature a research, like a review on something, but you want to filter out, like it's not just you go on PubMed and look for the words of interest, but then you also get like a bunch of articles that you don't actually need, and maybe there's no information that you really want. So I imagine the way you can apply this is that in the end you will get like a result that it will tell you like this is interesting, this is not. But I guess for that you have to train like some sort of regression model.
Yeah, so like if you had, you know, a group of papers that you knew were interesting, and you could like train a regression model to like be able to predict those papers are interesting and predict like maybe a negative sample are not interesting. you could also use clustering too. So like I showed, you could encode the abstract in an average of word embeddings. And let's say you knew a handful of papers that are interesting. Well, you could take the embeddings for the document embeddings, the average of the word embeddings for those abstracts, and rank how close other abstracts are to those abstract embeddings using cosine distance. And then that might help you filter out ones that aren't important and like prioritize ones that are important for you to look at sooner.
Mm-hmm.
Yeah, that's just one way of doing it.
Yeah, thanks.
Yeah.
Any other questions?
Oliver, this is great. What do you feel like are the best scientific corpuses for well, that are open, that are like downloadable, not your trust and stuff. That like is for I mean, there's PubMed, it's straight from PubMed, Wikipedia. What do you feel like other really good ones and can really have meaningful information?
Yeah. So, I mean, good corpora that are out there, like you mentioned, PubMed is a good one. Wikipedia is used pretty often. I think there are also some Twitter and Reddit corpora out there, but I don't know if anyone here would do research on that. Just off the top of my head, like Archive is some good stuff. There's also like a lot of this like people post anything there. So you might want to filter by if it's a paper that has a comment that mentions it was accepted to a certain conference or something like that. I should probably know other corpora you could use, but do clinical trials, do they have like descriptions and stuff? Because that might also be a corpora you could scrape too.
I'm pretty sure.
Yeah.
Yeah, that you could. There are some databases that, like the acronym is AACT, that has the clinical trial information in more of a structured format. So I'm not sure how much of the descriptions they have, but actually there are some fields that contain descriptions of the trials. But I bet there's other sources for like more of the info for a trial.
Yeah. Yeah. Another good corpus is Mimic. If you're doing anything with like clinical data, Mimic has like clinical notes that you can request access to, and they're de-identified. They're great to use too. Yeah.
You don't have anyone that's done embeddings on drug labels, like SPL, the structured product labels, but like I know there's an open FDA initiative on the platform that has like all the FDA labels on there, and I think they're more accessible if they're in JSON. I'm actually trying to get those. I'm almost there. I'm actually going to spend some time today to parse it. But yeah, I think those would be really useful too.
Yeah. Yeah, that makes sense. Yeah.
All right. Yeah, this was great. Looks like a few people hopped off already, but thanks, thanks guys for coming, and I want to say thank you to Oliver for a really excellent first tutorial for the Data Science Club this year.
Thank you so much.
And
absolutely.
really thank you all. It was great. Yeah, like we said, the recording we hope to make available, and we hope to do more of these in the future.
Great. Thanks for all for doing it, and thanks everyone for stopping by.
Yeah, thank you. Okay.
Thank you so much, guys. Have a nice day.
You too.
Bye-bye.
See you.